2017, headlines around the world announced that physicists had officially debunked the simulation hypothesis. The story ran in Popular Science, Newsweek, Motherboard, dozens of outlets, all of them citing a paper by two theoretical physicists named Zohar Ringel and Ringel-Kovrizhin, published in Science Advances. The takeaway in every article was the same. We can all relax. Science has proven we are not living in a computer simulation. The story got millions of clicks. It was shared across social media as definitive proof that the whole simulation idea was dead. And then everybody moved on. There is one problem with this. Ringel and Kovrizhin never said that. Their paper never once mentions the simulation hypothesis. It never claims to debunk anything about whether we live in a simulated universe. What their paper actually demonstrates is that a specific class of quantum systems, those exhibiting what is called the quantum Hall effect and certain gravitational anomalies, cannot be efficiently simulated using a specific classical algorithm called quantum Monte Carlo. That is it. That is the entire scope of the paper. One algorithm, one class of systems, one computational method. Scott Aaronson, one of the world's leading experts in computational complexity theory at the University of Texas at Austin, read the coverage and publicly corrected it on his blog. He pointed out that the paper is, in his words, entirely innocent of the language and tools of complexity theory. It says nothing about quantum computers, nothing about alternative algorithms, nothing about the broader question of whether a sufficiently advanced civilization could simulate a universe. The debunking was invented by science journalists who either did not read the paper or did not understand it, and the correction never went viral. The debunking of the debunking got a fraction of the attention, which means right now millions of people believe the simulation hypothesis was scientifically disproven. It was not even close. But here is where it gets worse. The paper that supposedly killed the simulation argument actually strengthened one of its most disturbing premises. Because what Ringel and Kovrizhin proved is that certain features of our universe are exponentially hard to simulate with classical computers. The computational complexity of quantum physics is not a weakness of the simulation hypothesis. It is a feature of the universe itself. And if you understand what that means, you understand why the people who actually work on the mathematics of information and computation are not laughing at the simulation argument. They are quietly unsettled by it. The simulation hypothesis did not die in 2017. What died was the public's willingness to take it seriously. And in the years since that fake debunking, the actual physics has gotten significantly worse. Not worse as in less rigorous, worse as in more uncomfortable, more convergent, more difficult to dismiss. You probably think you know what the simulation argument says. A philosopher named Nick Bostrom wrote a paper claiming we might live in a computer. Elon Musk said the odds are 1 billion to 1. The Matrix made it cool. And then serious physicists rolled their eyes, and the whole thing faded into the same category as flat Earth and ancient aliens. That is the version of the story you were given. And almost every part of it is wrong. What you were not told is that in the years since those headlines declared the debate over the physics of information has undergone a quiet revolution. In 2015, researchers proved that space-time is structured as a quantum error-correcting code. In 2019, the resolution of the black hole information paradox confirmed that the universe never destroys information under any circumstances. In 2022, a physicist proposed an experiment to measure the mass of a single bit of information. In 2023, a Nobel laureate published a book arguing that quantum mechanics emerges from cellular automaton processes at the Planck scale. None of this made the front page. None of it was connected to the simulation hypothesis in the press. But it should have been, because what these results collectively demonstrate is that the universe, at its most fundamental level, behaves less like a collection of matter and more like a running program. And the people publishing these results know it. They have known for years, and they are very, very careful about what they say in public. Bostrom's paper, published in 2003 in the Philosophical Quarterly, is not a claim that we live in a simulation. It is a logical argument structured as a trilemma, meaning it proves that at least one of three propositions must be true. The paper has been cited thousands of times. It has been attacked by some of the sharpest minds in physics and philosophy for over 2 decades, and the trilemma itself has never been formally refuted. Not once. Not by anyone. The 3 propositions are these. 1. The fraction of human-level civilizations that survive long enough to develop the computing power needed to run detailed simulations of conscious minds is very close to 0, meaning we go extinct, or something equivalent, before we ever get that capable. 2. The fraction of civilizations that reach that level of computing power but choose not to run such simulations is very close to 0, meaning they could do it, but virtually none of them want to. 3. The fraction of all conscious beings who are living in a simulation is very close to 1. At least one of those 3 statements is true. That is not a belief. That is what the math requires, and nobody has found a way around it. The mathematical core is cleaner than you would expect from a philosophy paper. Bostrom defines 3 variables. The fraction of civilizations reaching post-human capability, called F sub p. The fraction of those civilizations interested in running ancestor simulations, called F sub I. And the average number of simulations run by each interested civilization, called N sub I. The formula for the fraction of all observers living in a simulation is F sub sim equals the product of those 3 variables divided by the product of those 3 variables plus 1. The reason the argument is so hard to escape is the size of N sub I. Bostrom estimates that a single planet mass computer operating within known physics could simulate the entire mental history of humankind using less than 1/millionth of its processing power for 1 second. If even a small number of civilizations reach that capability and choose to run such simulations, the number of simulated minds would outnumber biological minds by factors so large that the probability of being biological approaches 0. You are either in a species that goes extinct before reaching that level of technology, or in a species that reaches it but never runs the simulations, or you are almost certainly simulated yourself. The argument does not require that consciousness is easy to simulate. It does not require that the simulators are simulating the entire universe, atom by atom. It only requires what Bostrom calls substrate independence, the assumption that conscious experience can arise on any computational platform that implements the right functional organization, at whatever level of detail that requires. This is not a radical assumption. It is the working assumption of most neuroscientists and AI researchers. If you believe a brain made of neurons can be conscious, and that consciousness depends on what the neurons do rather than what they are made of, you have already accepted substrate independence. And here is the part of the argument that almost nobody in the public conversation seems to have noticed. The argument does not need you to believe we are simulated. It only needs you to accept that at least one of the three propositions is true. If you reject proposition 3, you are forced into proposition 1 or 2. Either advanced civilizations always destroy themselves before reaching sufficient computing power, or they reach that power and universally choose not to use it for simulations. Both of those are extraordinary claims about the fate of all intelligent life in the universe, and neither one has any evidence supporting it. Bostrom himself assigns only about 20% probability to us actually being simulated. He is not a true believer. He's a logician who built an argument that nobody has been able to break. And that fact makes people uncomfortable. So they pretend it has been broken when it has not. But here is what nobody tells you when they discuss this argument. And it is the thing that should bother you more than the argument itself. The simulation hypothesis is a question about philosophy and probability. It lives or dies on logic. The part that is getting worse is not the philosophy, it is the physics. Because over the past 2 decades, physicists working on completely unrelated problems in black hole thermodynamics, quantum information theory, holography, and the foundations of space-time, have independently and repeatedly confirmed that the universe, at its most fundamental level, is built from information. Not metaphorically, not as an analogy, as a literal description of what the equations say. And the deeper they go into those equations, the harder it becomes to define what the word real even means. Think about what that means for a moment. The simulation argument is a philosophical question. You can agree or disagree with its premises. You can assign it whatever probability you want. But the physics underneath it, the physics that describes how information behaves in this universe, is not a matter of opinion. It is experimental. It is measured. It is confirmed. And it points with increasing precision toward a conclusion that makes the entire question of simulated versus real incoherent. The standard move when confronted with the simulation argument is to say something like, "That is unfalsifiable, therefore it is not science, therefore I do not have to think about it." Sabine Hossenfelder, a respected theoretical physicist at the Frankfurt Institute for Advanced Studies, has made this exact argument publicly, calling the simulation hypothesis pseudoscience in a widely shared article. And she is right that the hypothesis itself is unfalsifiable in any straightforward sense. You cannot design an experiment that proves you are not in a simulation, because any result could be explained as part of the simulation. But that critique, while valid on its own terms, misses something crucial. The simulation hypothesis is unfalsifiable. The physics of information is not. The Bekenstein bound is not a speculation. Landauer's principle is not a thought experiment. The holographic principle is not a metaphor. Quantum error correction in space-time is not a fringe idea. These are published, peer-reviewed, experimentally grounded results from mainstream physics, and what they collectively describe is a universe whose fundamental architecture is informational, computational, and eerily consistent with what a simulated universe would look like from the inside. Nobody planned this. Nobody set out to find evidence for simulation theory. These results emerged independently from black hole physics, quantum information theory, cosmology, and the foundations of quantum mechanics. Different researchers, different institutions, different decades. The convergence is accidental. And that is exactly what makes it so difficult to dismiss. So here is what we are going to do. We are going to follow this thread all the way down. Not the pop science version, not the Elon Musk soundbite, not the breathless headlines. We are going to look at Bostrom's actual math and what his critics actually conceded when they tried to tear it apart. We are going to trace the physics of information from a German engineer building computers in his parents' living room while Allied bombs fell on Berlin, through a grieving physicist at Princeton whose brother's death drove him to ask whether reality is built from yes or no questions, all the way to a 2015 paper that proved space-time itself operates as an error-correcting code. And we are going to watch, step by step, as the line between the universe is a computation and the universe is a simulation dissolves, not because anyone is trying to prove simulation theory, but because the physics will not let the distinction survive. The first thing you need to understand about Bostrom's argument is that almost nobody who criticizes it has actually engaged with the math. They attack the vibes. They attack the cultural associations. They attack the fact that Elon Musk talks about it at parties. What they do not do, with very few exceptions, is identify a specific step in the logical structure where the reasoning fails. And there is a reason for that. The reasoning does not fail. It is airtight within its assumptions. The only way out is to reject one of the assumptions, and every available rejection comes with its own disturbing implications. Nick Bostrom was born on March 10, 1973, in Helsingborg, Sweden. He studied philosophy, mathematics, and mathematical logic at Stockholm University, then earned a PhD in philosophy from the London School of Economics in 2000. By 2003, he was at Oxford, where he founded the Future of Humanity Institute. He is not a physicist. He is not a computer scientist. He is a philosopher who happens to be exceptionally good at math. And the paper he published that year in the Philosophical Quarterly has become one of the most cited and most misunderstood documents in modern intellectual history. The argument's power comes from a single insight about numbers. If a post-human civilization runs ancestor simulations, the number of simulated minds it creates will be enormous. Not large, enormous. Bostrom estimates that a single planetary mass computer, using technology consistent with known physics, could run roughly 10 to the 33rd operations per second, running a simulation of the entire history of human consciousness. Roughly 10 billion brains, running for roughly 50 years each, would require something on the order of 10 to the 36th operations. That is less than 1/1,000,000th of 1 second of the computer's total capacity. One civilization could run millions of such simulations as a rounding error on its total computational budget. If even a small fraction of post-human civilizations choose to do this, the total number of simulated minds across all civilizations would dwarf the number of biological minds that have ever existed by factors of millions, by factors of billions. The math does not care about your intuitions. If the simulations are run, the simulated observers outnumber the real ones so overwhelmingly that a randomly selected observer, meaning you, is almost certainly in a simulation. The only exits are the two other propositions. Either civilizations never reach post-human capability, which means something, probably something catastrophic, prevents them, or they reach it and universally decline to run such simulations, which means something about the nature of advanced intelligence makes ancestor simulations repulsive or impossible. Both of those exits are themselves extraordinary claims. Neither has evidence. and both say something deeply uncomfortable about the future of our species. Now here is where it gets important. The critics, because Bostrom's argument has drawn fire from serious people, and understanding what they actually conceded in the process of attacking it is as revealing as the argument itself. Sean Carroll, the theoretical physicist at Johns Hopkins, identified what he called a logical contradiction in the argument. His critique, published on his blog in August of 2016, works like this. The simulation argument starts by assuming that creating simulations is computationally easy. It concludes that we are probably in a lowest level simulation, the bottom of the stack. But a lowest level simulation, by definition, does not have the resources to create its own simulations, which contradicts the opening premise that simulations are common. Carroll's objection is clever, but notice what it concedes. It accepts that the computational requirements are feasible. It accepts the substrate independence assumption. It accepts the statistical reasoning. It only disputes the self-consistency of the nesting. And Bostrom has addressed this. The argument does not require infinite nesting. It only requires that the simulators at the top level have sufficient resources, and a single level of simulation is enough to make the statistics overwhelming. Lisa Randall, the Harvard physicist, was more blunt. At the 2016 Isaac Asimov Memorial Debate at the American Museum of Natural History, she rated the probability of living in a simulation as effectively zero. She called the idea that simulators would create our specific reality audacious and ridiculous. Her argument boils down to motivation. Why would an advanced civilization bother simulating us? We are not interesting enough. This is a fine objection as far as it goes, but it is an argument about alien psychology, not about physics or logic. Randall offers no physical reason why simulation is impossible. She simply finds it implausible that anyone would want to. That is an opinion, not a refutation. Hossenfelder's critique is the sharpest and the most revealing. She calls the simulation hypothesis pseudoscience because it cannot be falsified and because invoking a programmer is functionally identical to invoking God. She is right about the unfalsifiability, but here is the part she does not say out loud. Her exact objection applies with equal force to the string theory landscape, which posits roughly 10 to the 500 possible vacuum states, none of which can be individually tested. It applies to eternal inflation and the multiverse. It applies to Boltzmann brains. These ideas are debated respectfully in physics departments around the world. They receive grant funding. They fill tenured positions. The simulation hypothesis gets the same unfalsifiability critique and is dismissed as not even worth discussing. The inconsistency should bother you, regardless of where you land on the question itself. And then there is David Kipping's paper, published in 2020 in the journal Universe. Kipping applied proper Bayesian statistics to Bostrom's trilemma. The popular claim, repeated by Musk and others, is that the odds of being in a simulation are billions to 1. Kipping showed this is wrong. When you apply the correct Bayesian framework, the maximum probability you can assign to the simulation hypothesis, given the structure of Bostrom's argument, is 50%. Not billions to 1, 50-50. This is lower than the hype. But think about what 50-50 means for a hypothesis that was supposedly debunked. 50% probability assigned by rigorous Bayesian analysis to an idea the media told you was dead. That is not a debunking. That is an open question, as open as any question in science. The 2016 Isaac Asimov Memorial Debate at the American Museum of Natural History crystallized where the intellectual community actually stands on this, as opposed to where the media portrays it standing. Neil deGrasse Tyson moderated a panel that included David Chalmers, Lisa Randall, Max Tegmark, Zohreh Davoudi, and S. James Gates Jr. When Tyson polled the audience and panel on the probability that we live in a simulation, he noted that the views ranged from essentially 0 to roughly 50-50, with Tyson himself at 50%. Gates, a theoretical physicist at the University of Maryland who has spent decades studying supersymmetry, offered a detail that silenced the room. In the course of his research on the equations of fundamental physics, Gates found what he described as error-correcting codes, specifically block linear self-dual error-correcting codes, embedded in the equations of supersymmetric string theory. These are not metaphors. They are the same mathematical structures used in computer science to protect data integrity. Gates made clear he was not claiming this proves simulation, but he admitted that discovering browser-style error-correcting codes inside the fundamental equations of physics gave him pause. The response to the debate was telling. Media coverage framed it as entertainment, as scientists having fun with a wild idea. But if you watch the full recording, the tone in the room was not playful. It was uncomfortable. These are people who understand the math, and the math was not cooperating with the dismissal that the public expected. The cultural trajectory of the simulation hypothesis is itself revealing. It has followed a pattern that historians of science would recognize. An idea is proposed. It is initially treated as clever, but unserious. It gains traction in popular culture, which causes the scientific community to distance itself further, not because the idea has been refuted, but because association with pop culture is professionally toxic. Meanwhile, the actual evidence quietly accumulates. The idea enters a zone where it is simultaneously too famous to be taken seriously and too rigorous to be dismissed. Bostrom's argument is stuck in that zone. It has been stuck there for 20 years, and the longer it stays there without being refuted, the more the silence around it starts to look less like indifference and more like avoidance. Here is the misconception you need to correct before we go any further, because it poisons every public discussion of this topic. The simulation argument and the simulation hypothesis are not the same thing. Bostrom's trilemma says that at least one of 3 propositions must be true. The simulation hypothesis is only proposition 3, the claim that we are actually living in a simulation. Almost every popular critique attacks proposition 3, and almost none of them address the trilemma itself. You can reject the idea that we are simulated, and the trilemma still stands. You just have to live with proposition 1 or proposition 2 instead, and those are not comfortable places to live. Proposition 1 means advanced civilizations always fail. Proposition 2 means advanced civilizations universally choose not to explore their own origins through simulation, which is a statement about the psychology of every sufficiently advanced species in the cosmos. A claim so bold, it should require its own evidence. The argument is not dead. The argument has never been healthier. And the reason the physics community avoids engaging with it publicly is not that they have found the flaw. It is that they have not found the flaw, and acknowledging that openly is professionally dangerous. You do not get tenure by saying we might be in a simulation. You get tenure by studying quantum error correction and the holographic principle and the information content of black holes, which, as it happens, are the exact fields whose results keep making the simulation argument harder to dismiss. But here is the thing. Bostrom's argument lives entirely in the world of logic and probability. It does not need physics to work. It stands on its own mathematical legs. So why does the physics matter? Because the argument's strongest premise, substrate independence, the idea that consciousness can run on any sufficiently complex computational system, was always the weakest link. If you could prove that consciousness requires something non-computational, something that cannot be replicated by any machine regardless of its sophistication, the entire argument collapses. And for 20 years, nobody has proven that. Instead, the physics has gone in the opposite direction. It has increasingly confirmed that the fundamental constituents of reality are not matter and energy in the way you were taught. They are information, and the universe processes that information according to rules that are, at every level, physicists can currently probe, computational. That is not a metaphor. That is not a philosophical claim. That is what the equations say, and it is where the story of the simulation argument stops being philosophy and starts being physics, because the question is no longer whether Bostrom's logic is valid. The question is whether the universe itself is built in a way that makes the distinction between real and simulated meaningful. And to answer that question, we need to go back to 1938, to a young German engineer in his parents' apartment in Berlin, cutting 30,000 metal parts by hand with a jigsaw while the world prepared for war. Konrad Zuse was born on June 22, 1910, in Berlin. He was a quiet, artistic child who loved painting and theatre. He studied civil engineering at the Technische Hochschule in Berlin-Charlottenburg, and he hated every minute of it. Not the ideas, the calculations, the endless, tedious hand-cranked arithmetic that engineering required in the 1930s. Stress calculations for buildings, load-bearing computations for bridges. Each one took hours of manual labor with paper and pencil. And Zuse, who was by all accounts a profoundly lazy man in the best sense of the word, looked at that mountain of calculation and thought there had to be a better way. In 1936, he quit his job as a structural engineer at the Henschel aircraft factory and moved back into his parents' apartment on Rangelstrasse in Berlin. There, in their living room, he began building a machine that could calculate automatically. He had no knowledge of Charles Babbage. He had never heard of Alan Turing, whose foundational paper on computability was published that same year. He was working in complete intellectual isolation, reinventing the concept of a programmable computer from scratch, using nothing but scrap metal and his own stubbornness. The machine was called the Z1. It consisted of roughly 30,000 metal parts, each one cut by hand, with a jigsaw assembled into a mechanical device that filled most of the living room. His parents tolerated this. The Z1 was completed in 1938. It was unreliable, prone to jamming, but it worked. It could perform binary arithmetic. It could be programmed using punched tape. It was, in principle, the first freely programmable computer ever built, and almost nobody noticed. The Z3 followed in 1941, built from scavenged telephone relays because metal was rationed for the war effort. Completed on May 12th of that year, the Z3 was the world's first fully functional, programmable, electromechanical computer. It could perform floating point arithmetic. It could be programmed for different tasks, and it was assembled in wartime Berlin under a regime that had no interest in funding theoretical computation and every interest in building weapons. Allied bombing destroyed the Z3 in late 1943, along with all its documentation. The Z1 and its blueprints had already been destroyed on January 30th, 1944. When the Nazi government offered to relocate Zuse's work to the Dora Mittelbau concentration camp, where V2 missiles were being assembled with slave labor, Zuse refused. He gathered his latest machine, the Z4, loaded it onto a military truck, and fled south with his pregnant wife, eventually hiding the computer in a barn in the Aargau Alps, in the tiny village of Hinterstein. There he waited out the end of the war. Here is the part that matters for our story. In 1967, almost 3 decades after building the Z1, Konrad Zuse published a paper called Rechnender Raum, which translates to calculating space, in the journal Elektronische Datenverarbeitung. It was expanded into a book in 1969. In it, Zuse proposed something that nobody in science was prepared to hear. He proposed that the entire universe is a cellular automaton, that physics itself is a form of computation, that the laws of nature are not descriptions of how the universe behaves, but instructions that the universe executes step by step in a vast, ongoing calculation. This was the first work on what would later be called digital physics, and it was received with near total silence. Zuse wrote in German. The computer science world was English-speaking. The physics world dismissed the idea as metaphysical speculation, unworthy of serious engagement. There was a reason for this, beyond language. In the late 1960s, physics was triumphant. The standard model was being assembled. Particle accelerators were producing new discoveries every year. Nobody in mainstream physics felt the need to ask whether the universe was a computation, because the standard methods worked so well. The question seemed unnecessary. It seemed like philosophy, not physics, and in the culture of post-war physics, that is, philosophy was a dismissal, not a description. Zuse's reasoning, laid out carefully in Rechnender Raum, was more rigorous than his critics gave him credit for. He noted that the laws of physics are discrete at the quantum level. He noted that physical processes evolve in steps that can be described algorithmically. He noted that cellular automata, simple grids following simple rules, could generate complexity indistinguishable from natural phenomena. His proposal was not that the universe is metaphorically a computer. It was that the distinction between a physical law and a computational rule is a distinction without a difference. If the laws of nature can be expressed as algorithms, and if the state of the universe at any moment can be expressed as data, then the evolution of the universe from one moment to the next is computation, regardless of whether anyone intended it to be. Maurice Wilkes, the British computing pioneer, later observed that Zuse suffered from being in the wrong country at the wrong time. The man who invented the computer, who built it while bombs fell on his city, who hid it in a barn rather than let it serve a death camp, also became the first person to propose that the cosmos itself runs on computation. And nobody listened. The irony is almost too precise. The inventor of the machine proposed that the universe is one, and the world that built a $1 trillion industry on his invention could not take the idea seriously. Edward Fredkin picked up where Zuse left off, and he brought something Zuse never had: access to the American academic establishment and the sheer force of personality to make people listen. Fredkin was a former Air Force fighter pilot who dropped out of Caltech after 1 year at age 19. Founded a company called Information International that made him a millionaire, and then talked his way into directing MIT's Project Mac, one of the most important computer science programs in the world, without ever finishing his undergraduate degree. He was brilliant, eccentric, and completely unbothered by academic conventions. In the 1990s, Fredkin proposed what he called finite nature, the hypothesis that at the most fundamental level, the universe consists of a finite number of bits being processed by deterministic rules. Every volume of space-time in Fredkin's framework contains a finite amount of information, and the evolution of the universe is the execution of a cosmic algorithm. His Fredkin gate, a 3-bit universal reversible logic gate, demonstrated that computation can proceed without destroying information, a result that would prove deeply relevant to later discoveries about black holes and entropy. What made Fredkin unusual, even among his fellow digital physics enthusiasts, was his willingness to follow the logic to its endpoint. He argued that at the most fundamental level, the difference between a universe that is a computation and a universe that is being computed is meaningless. If the laws of physics are computational rules, and the state of the universe is data being processed by those rules, then the universe is, by definition, a running program. Whether anyone designed that program, or whether it simply exists as a mathematical structure, the computation is real either way. Fredkin was saying this in the 1990s, 2 decades before the debate became culturally visible, and the physics community treated him as an interesting eccentric rather than a serious theorist. He died in June 2023 at the age of 88, having lived just long enough to see the ideas he championed move from the fringe toward the uncomfortable center of theoretical physics. The intellectual lineage here is important to trace because it is not a straight line. Zuse worked in isolation in wartime Germany and was ignored. Fredkin worked at the intersection of computer science and physics at MIT and was tolerated as a curiosity. It took a physicist of towering stature and deep personal anguish to drag these ideas into the mainstream of physics itself. But the figure who did more than anyone else to bring information to the center of physics was John Archibald Wheeler, and Wheeler's story cannot be separated from his grief. Wheeler was born on July 9th, 1911, in Jacksonville, Florida. He earned his PhD at age 21 from Johns Hopkins, studied under Niels Bohr in Copenhagen, and went on to become one of the most influential physicists of the 20th century. He coined the terms black hole, wormhole, and quantum foam. He supervised the PhD theses of Richard Feynman, Hugh Everett III, Kip Thorne, and Jacob Bekenstein, 4 students who between them would reshape the foundations of quantum mechanics, quantum gravity, and black hole physics. Wheeler worked on the Manhattan Project at Hanford, helping design the plutonium production reactors that produced the material for the bomb dropped on Nagasaki. Wheeler had a younger brother named Joe. Joe Wheeler earned a PhD in American history, had a wife and a young child, and enlisted in the army to fight in World War II. While John was at Hanford, racing to produce plutonium that might end the war, Joe was sent to Italy. Joe sent John a 2-word postcard. It said, "Hurry up." John did not know that when the postcard arrived, Joe was already dead, killed in combat in a foxhole near Florence in 1944. Wheeler carried this for the rest of his life. He later wrote that an atomic bomb program started a year earlier and concluded a year sooner would have spared 15 million lives, including his brother Joe's. His daughter recalled that as he got older, he wept often over this brother. Princeton's obituary noted that despite his sunny disposition, he carried with him a secret sadness. And that sadness, that obsession with time and whether the past could have gone differently, fed directly into the question that consumed the last decades of Wheeler's career. A question he distilled into 3 words in 1989 in a paper presented at the Santa Fe Institute. It from bit. Those 3 words are among the most consequential in the history of physics. Wheeler wrote, "Every it, every particle, every field of force, even the space-time continuum itself, derives its function, its meaning, its very existence entirely, even if in some contexts, indirectly, from the apparatus elicited answers to yes or no questions, binary choices, bits. The universe," Wheeler argued, "is not made of stuff. It is made of information. Particles are not little balls of matter. They are answers to yes or no questions. The distinction between physics and information is not a boundary between 2 different things. It is a failure of human categories that do not apply at the fundamental level." Wheeler did not use the word simulation. He did not need to. What he described was a universe whose substance is informational, whose dynamics are computational, and whose existence depends on observation. He called it the participatory universe, the idea that observers are not passive witnesses, but active participants in bringing reality into being. This was not mysticism. It was Wheeler's interpretation of quantum mechanics, grounded in decades of work on the foundations of the theory. And it came from a man who had spent his life haunted by questions about whether the past is fixed, whether time is what it appears to be, and whether reality has an existence independent of the minds that perceive it. Wheeler's student Jacob Bekenstein turned it from bit into mathematics. In 1972, working as Wheeler's graduate student at Princeton, Bekenstein proposed that black holes have entropy and that this entropy is proportional to the surface area of the event horizon. This was heresy. Stephen Hawking initially rejected the idea. If black holes have entropy, they must have temperature. If they have temperature, they must radiate. And nothing, according to general relativity, can escape a black hole. Hawking set out to prove Bekenstein wrong, and ended up proving him right. Hawking's own 1975 calculation showed that black holes do radiate at a temperature exactly consistent with Bekenstein's entropy formula. The student had outpaced the master. The Bekenstein-Hawking entropy formula is this: the entropy of a black hole equals its event horizon area divided by 4 times the Planck area. This is remarkable for several reasons. First, the entropy scales with the surface area, not the volume. A black hole is a 3-dimensional object, but its information content is encoded on a 2-dimensional surface. Second, the entropy is finite. A black hole of any given size contains a maximum fixed amount of information. Third, and this is the part that matters most for our story, a black hole is the densest possible information storage device in the universe. It saturates what is called the Bekenstein bound, the absolute upper limit on the information that can be contained within any region of space with a given energy. Bekenstein published the bound in 1981 in Physical Review D. The formula is S less than or equal to 2 pi k RE divided by h bar c, where S is entropy, r is the radius of the region, and E is the total energy contained within it. Horacio Cassini rigorously proved the bound in 2008 using quantum field theory methods, removing the last doubts about its validity. It is now universally accepted, and its implication is stark. Jacob Bekenstein was born on May 1st, 1947 in Mexico City to Polish Jewish immigrants who had fled Europe. He grew up speaking Yiddish and Spanish before learning English. He moved to the United States for graduate school, arriving at Princeton, where Wheeler took him on as a student. Bekenstein was quiet, methodical, and startlingly original. When he proposed that black holes have entropy, he was contradicting the received wisdom of the entire general relativity community. Hawking was not just skeptical, he was openly dismissive. The idea that a black hole, the ultimate destroyer, could have a well-defined entropy seemed absurd. Then Hawking's own calculation vindicated Bekenstein, and the student who had dared to disagree with the most famous physicist alive was proved right. The Bekenstein bound does not merely constrain black holes, it constrains everything. The observable universe has a finite boundary, the cosmic horizon at roughly 46 billion light-years. It has a finite energy. Therefore, by the Bekenstein bound, it contains a finite amount of information. Not approximately finite, exactly finite, bounded by a specific formula with specific physical constants. The universe is not infinite in its informational content. It is bounded, it is countable, it is in principle storable. And that is the single most important fact for the simulation question, because a universe with infinite information content could not, even in principle, be simulated. A universe with finite information content can be. Not easily. Not by us. But the door that infinite information would have permanently sealed is, by Bekenstein's formula, permanently open. Seth Lloyd put a number on it. Lloyd, a professor of mechanical engineering at MIT and a pioneer of quantum computing, published a paper in 2002 in Physical Review Letters titled Computational Capacity of the Universe. He calculated that the observable universe registers approximately 10 to the 90 bits of information, or roughly 10 to the 120 bits when gravitational degrees of freedom are included. The universe has performed no more than 10 to the 120 elementary logical operations since the Big Bang. In his 2006 book, Programming the Universe, Lloyd framed this with characteristic bluntness. Atoms and electrons are bits. Atomic collisions are operations. Machine language is the laws of physics. To understand how large these numbers are and why they matter, you need to feel the gap between what the universe does and what humanity can do. The most powerful supercomputer on Earth, as of 2025, performs roughly 10 to the 18th floating point operations per second. That is 1 exaflop. If you ran that supercomputer for the entire age of the universe, 13.8 billion years, it would perform approximately 4 times 10 to the 35th total operations. The universe has performed 10 to the 120th. The gap between our best computer, running for the entire age of the cosmos, and the universe's total computational output is roughly 10 to the 85th. That is a 1 followed by 85 zeros. To put that in perspective, the total number of atoms in the observable universe is approximately 10 to the 80. You would need more computers than there are atoms in the universe, each running for longer than the universe has existed, to match what the universe computes by simply existing. This is usually presented as an argument against simulation, The universe is too computationally complex to simulate. But that framing assumes the simulator needs to match the universe's own computational scale with classical hardware operating under our physics. It assumes the simulation runs at full fidelity, everywhere, all the time. The holographic principle already tells us this assumption is wrong. The information content of a volume is encoded on its surface, not distributed through its bulk. The universe is already, in a precise physical sense, data compressed, and the measurement problem tells us the universe does not resolve definite states until observation forces it to. If you only need to compute what is observed, the computational requirements drop by orders of magnitude that nobody has bothered to calculate. Lloyd was also the first to ask a question that remains underexplored. If the universe is performing 10 to the 120th operations, what is it computing? Not what do we observe it doing? What is the computation for? In a conventional physical universe, the question does not arise. Physics just happens. There is no purpose, no output, no answer being generated. But if the universe is performing computation in the mathematical sense of the word, then by definition, that computation has a result. What is the result? Lloyd does not answer this. Neither does anyone else. The question hangs there, unanswered, in the most respected quantum information journal in the world. These are not analogies. Lloyd is not saying the universe is like a computer. He is saying the universe is performing computation by the mathematical definition of computation, and has been since the moment it began. And then there is Landauer's principle, which is the piece that connects information to the physical world in a way that cannot be argued away. Rolf Landauer, working at IBM in 1961, proved that erasing one bit of information requires a minimum energy dissipation of kT times the natural logarithm of 2, approximately 2.87 times 10 to the negative 21 joules at room temperature. This is not a theoretical limit. It has been experimentally verified, first in 2012 by Barut and colleagues, published in Nature, using a silica bead trapped by optical tweezers. Then in 2014, with nanomagnetic memory bits. Then in 2018, with trapped calcium ions in a fully quantum system. Each verification confirmed Landauer's number with increasing precision. The implication of Landauer's principle is this: information is physical. It is not an abstraction. It is not a mathematical convenience. Erasing a bit of information produces a measurable, detectable physical change in the world. Information has thermodynamic consequences. It costs energy to destroy. It is as real as mass, as real as charge, as real as anything in physics. When you combine the Bekenstein bound with Lloyd's calculations and Landauer's principle, the picture that emerges is not metaphorical. The universe contains a finite amount of information. That information is physical. The universe processes that information according to the laws of physics, and the processing capacity of the universe is finite and calculable. Wheeler's it from bit is not poetry. It is the accurate description of what the mathematics says about the fundamental nature of reality. And if computation and physical reality are the same process, if what the universe does is computation, then you need to answer a question that nobody in mainstream physics is willing to answer publicly. What exactly would make a simulation different from a universe? That question is going to hang in the air for a while, because the answer requires going deeper into what physicists have found about how the universe stores, processes, and protects its information. And what they have found is, if anything, more unsettling than everything we have covered so far. In 1993, a Dutch physicist named Gerard 't Hooft published a paper that should have changed everything. It was titled Dimensional Reduction in Quantum Gravity, and it proposed something that sounds impossible. The total information contained in a three-dimensional volume of space, every particle, every field, every possible quantum state can be fully described by information encoded on the two-dimensional boundary of that volume. One bit of information per Planck area, which is roughly 10 to the negative 70th square meters, the smallest meaningful unit of surface in the universe. 't Hooft is not someone the physics community can ignore. Born on July 5, 1946 in Den Helder, Netherlands, he won the Nobel Prize in Physics in 1999 with Martinus Feldman for elucidating the quantum structure of electroweak interactions. His great-uncle Fritz Zernike also won a Nobel for the phase contrast microscope in 1953, making them one of a very small number of families with multiple laureates. When his elementary school teacher asked young Gerard what he wanted to be when he grew up, he answered, "A man who knows everything." He has spent his career trying to fulfill that promise, and it has led him to conclusions that most of his colleagues would rather not confront. Leonard Susskind at Stanford gave 't Hooft's idea a rigorous mathematical framework in 1995, publishing in the Journal of Mathematical Physics. Together, their work established what is now called the holographic principle. The name comes from the technology behind holograms, where a 2D surface encodes all the information needed to reconstruct a 3D image. The physics version says the same thing applies to the universe itself. The information in any volume of space is not stored throughout the volume. It is stored on the surface. The three-dimensional world you experience is, in a precise physical sense, a projection from a two-dimensional boundary. Think about what this means for the computational requirements of simulating the universe. The naive estimate, based on tracking every particle in a three-dimensional volume, requires processing on the order of 10 to the 90 bits. That is the number that makes simulation seem impossible. But the holographic principle says, you do not need to simulate the volume, you only need to simulate the surface. And the surface of a sphere grows as the square of the radius, while the volume grows as the cube. The reduction in computational requirements is not a factor of 10 or 100. It is a reduction by entire dimensions of complexity. The universe has built itself in a way that makes it dramatically more compressible, and therefore dramatically more simulable than anyone would have guessed before 1993. This would be strange enough on its own, but it got stranger in 2015. Ahmed Al-Mahiri, Shidong, and Daniel Harlow published a paper in the Journal of High Energy Physics that proved something about the structure of space-time that connects directly to computer science. They showed that the way space-time emerges from quantum information in the ADS/CFT correspondence, the mathematical duality between a theory of gravity and a theory of quantum fields on a boundary follows the exact mathematical structure of a quantum error-correcting code. If you have not encountered error-correcting codes before, here is the essential idea. Any communication system, any computer, any storage device that operates in a noisy environment needs a way to detect and fix errors. When you stream a video online, the data passes through cables and routers that occasionally corrupt a bit, flipping a 0 to a 1 or vice versa. Error-correcting codes add redundancy to the data in a structured way so that the receiver can detect corruption and reconstruct the original information even if some bits are damaged. Your phone does this. Your hard drive does this. Every digital device you own relies on error correction to function. Al-Mahiri, Dong, and Harlow showed that space-time does this too. The relationship between the quantum information on the boundary and the geometry of the interior, the way three-dimensional space emerges from two-dimensional data, is structured exactly like a quantum error-correcting code. The bulk geometry, meaning the three-dimensional space you live in, is a redundantly encoded version of the boundary data, meaning the two-dimensional information surface. Damage to some of the boundary information does not destroy the bulk geometry. The encoding is robust. It corrects errors. It protects the data. John Preskill, the Caltech physicist who won his bet with Hawking about black hole information, put it this way: entanglement is holding the space together. If you want to weave space-time out of little pieces, you have to entangle them in the right way. And the right way is to build a quantum error-correcting code. Let that sit for a moment. The fabric of space-time, the stage on which all of physics plays out, has the mathematical structure of an error-correcting code. Not approximately, not metaphorically, exactly the same mathematical structure that engineers use to protect data in computers appears independently and for no obvious reason in the fundamental architecture of reality. If someone told you they had discovered that a system stores information on a compressed two-dimensional surface, projects it as a three-dimensional reality, protects that information with error-correcting codes, and never, under any circumstances, allows information to be destroyed, you would say they were describing a computational system. That is what you would call it if you encountered it in any other context. But when physicists encounter these exact properties in the universe itself, they do not use that word. They use words like holographic duality and gauge gravity correspondence and information theoretic constraints, and they move on. The black hole information paradox reinforces this. In 1975, Hawking calculated that black holes radiate thermally, losing mass and eventually evaporating completely. The problem is that thermal radiation carries no information about what fell into the black hole. If a black hole evaporates completely and the radiation is truly thermal, then the quantum information about everything that ever crossed the event horizon is destroyed. This violates a fundamental principle of quantum mechanics called unitarity, which says that information is always preserved. Quantum mechanics says information is eternal. Black hole physics seemed to say information can be annihilated. On February 6, 1997, Hawking and Kip Thorne bet John Preskill that information falling into a black hole is permanently destroyed. The stakes were characteristically witty for physicists, an encyclopedia from which information can be recovered at will. The bet captured a genuine crisis in physics. If information can be destroyed, quantum mechanics is wrong at a fundamental level. If information cannot be destroyed, general relativity is wrong at a fundamental level. Both theories are among the most precisely confirmed in the history of science. Something had to give. For 7 years, the bet stood unresolved, representing one of the deepest unsolved problems in theoretical physics. Then, on July 21, 2004, at the GR17 conference in Dublin, Hawking conceded. He had been working on a new calculation that showed information could escape a black hole through quantum correlations in the Hawking radiation. He paid Preskill with a copy of Total Baseball, the ultimate baseball encyclopedia. Thorne, notably, did not concede. He was not satisfied with Hawking's argument and continued to believe information might be lost. The disagreement between Hawking and Thorne, two of the 20th century's greatest relativists, tells you how deep the crisis ran. But the mathematical resolution came later, and it is definitive. In 2019, work by Jeffrey Pennington and separately by Ahmed Almhiri, Netta Engelhardt, Donald Marolf, and Henry Maxfield introduced the concept of entanglement islands, regions inside the black hole interior, whose quantum information contributes to the entropy of the outgoing Hawking radiation. This work successfully reproduced the Page curve, the theoretical curve that describes how the entropy of the radiation first increases and then decreases as the black hole evaporates, exactly as quantum mechanics requires for information preservation. The significance of this cannot be overstated. For 40 years, the black hole information paradox was the central unresolved conflict in fundamental physics. Its resolution confirmed definitively that information is never destroyed. Not by black holes, not by anything. The universe keeps perfect records. Think about what that means for your life right now. Every photon that has ever bounced off your face, every sound wave your voice has ever produced, every neural firing in your brain, the information describing all of those events still exists somewhere in the universe, encoded in the quantum state of the Hawking radiation of whatever black hole eventually absorbs the matter you are made of. In principle, all of it is recoverable. Your entire history, down to every fleeting thought, is written into the fabric of reality in a way that cannot be erased. The universe does not forget. It is constitutionally incapable of forgetting. That is not mysticism. That is the direct implication of the Page curve calculation accepted by the mainstream of theoretical physics. A universe that stores information on surfaces, that projects 3 dimensions from 2, that corrects errors in its own fabric, that never, under any physical process, permits information to be lost. These are not properties anyone predicted from first principles. These are not properties anyone would expect of a universe that is simply there, a brute fact with no deeper explanation. These are properties you would expect of a system that was designed to preserve and process information reliably, a system with computational integrity. But perhaps you are not yet convinced. Perhaps you think this is an overinterpretation. The universe has these properties, but that does not mean it is a computation. It is just the way physics works. Fair enough. But consider the cumulative weight of what we have established so far. The universe has finite information content. That information is physical and has measurable thermodynamic properties. The universe processes this information according to calculable rules. The information in any volume of space is encoded on the boundary of that volume, not distributed through its interior. That encoding is structured as an error-correcting code, and information, once created, is never destroyed. If any single one of these facts were true in isolation, you could shrug it off. When all of them are true simultaneously, independently confirmed, and converging on the same structural description, shrugging requires more effort than engaging. And we have not yet discussed the most disturbing property of all. What happens when you look at how the universe treats observation? In quantum mechanics, particles do not have definite properties until they are measured. An electron does not have a definite position until something interacts with it in a way that extracts position information. Before measurement, the electron exists in a superposition of all possible positions, described by a wave function. Measurement collapses the wave function to a single outcome. This is not an edge case. This is the foundational, experimentally confirmed reality of quantum mechanics. Every quantum experiment ever performed is consistent with this description. Quantum entanglement reinforces how deep the information structure goes. When two particles become entangled, their quantum states become correlated in a way that persists regardless of the distance between them. Measure one particle, and you instantly know something about the other, whether it is across the room or across the galaxy. Einstein called this spooky action at a distance and thought it proved quantum mechanics was incomplete. Bell's theorem in 1964 and aspects experiments in 1982 proved Einstein wrong. The correlations are real. They are not transmitted by any signal traveling between the particles. They are a property of the information structure itself, a feature of how reality encodes relationships between its components. And then there is the no cloning theorem, proved independently by Wouters and Zurek, and by Dijks in 1982. It states that an arbitrary, unknown quantum state cannot be perfectly copied. This is not a practical limitation. It is a fundamental law. The universe has a built-in prohibition against duplicating quantum information. Think about what kind of system needs a no-copy rule. A system that treats information as a conserved resource. A system where duplication would create inconsistencies. A system that manages information integrity as a core function. The no-cloning theorem, the preservation of information by black holes, quantum error correction in space-time, and the holographic encoding of 3 dimensions on 2-dimensional surfaces are all features of one underlying reality. A reality that stores, processes, compresses, protects, and never destroys information. Every one of these features was discovered independently. Every one was a surprise. And collectively, they paint a picture that is becoming increasingly difficult to interpret as anything other than what it looks like. The simulation analogy writes itself. A system that does not compute definite outcomes until an observer demands them is a system that is conserving computational resources. It is rendering on demand. This analogy is imperfect, and physicists hate it for good reason. Quantum mechanics is not literally lazy rendering. The superposition is a real physical state with measurable consequences, such as interference patterns, but the structural similarity is there. And Wheeler's delayed choice experiment makes it harder to dismiss. Wheeler proposed his delayed choice experiment in 1978. The setup is a variation of the double slit experiment. A photon is sent toward 2 slits. If you place detectors at the slits, you can determine which path the photon takes, and the interference pattern disappears. The photon behaves as a particle. If you remove the detectors, the photon produces an interference pattern. It behaves as a wave. Wheeler's twist was to make the choice of whether to measure which path information after the photon has already passed through the slits. The decision about how to observe the photon is made after the photon has already done whatever it is going to do. The experiment was first performed by Alain Aspect in 1982 and has been replicated many times since with increasing sophistication. The result is unambiguous. The choice of observation made after the photon has already traversed the apparatus, determines whether the photon behaved as a wave or a particle. Wheeler's own summary was characteristically stark. We have to say that we decide what a photon shall have done after it has done it. The delayed choice quantum eraser, proposed by Scully and Druhl in 1982 and experimentally implemented by Kim and colleagues in 2000, pushed this even further. In this experiment, which path information is first recorded and then erased. When the information is erased, the interference pattern reappears, but only in the subset of data where erasure occurred. This has led to widespread claims that the quantum eraser proves retrocausality, that the future reaches back and changes the past. And here is a misconception that needs correcting, because dozens of YouTube videos get this wrong. The quantum eraser does not prove retrocausality. The interference pattern only appears when you select the subset of data corresponding to erased which path information, and that selection requires information from the future measurement. Without that selection, the total pattern shows no interference. What the experiment actually proves is something both subtler and, if you think about it carefully, more disturbing than retrocausality. It proves that what determines physical outcomes is not physical interaction. It is whether information exists. The universe does not care whether you physically disturb the photon. It cares whether which path information is available anywhere to anyone in any form. If that information exists, the photon is a particle. If that information is erased, the photon is a wave. The physical world is not responding to forces. It is responding to information. When physicists describe a universe that stores information on compressed surfaces, projects three-dimensional space from two-dimensional data, protects that information with error-correcting codes, never permits information to be destroyed, and only resolves physical outcomes based on whether information is available, they are describing something. They are describing a system with specific computational properties, and they know it. They have been publishing papers about these properties for 30 years. The holographic principle, ADS/CFT, quantum error correction in space-time, the black hole information paradox, and its resolution, the informational basis of quantum measurement. They just refuse to use the word. You would expect, after 30 years of these results accumulating, that the trajectory would start to level off, that someone would find the boundary where the information analogy breaks down, where the computational structure stops, where the universe reveals itself to be irreducibly physical in a way that no computational description can capture. That is what critics of the simulation hypothesis keep promising. The physics will eventually show the limits. The analogy will break. It has not. The math is getting worse. In 2019, Melvin Vopson, a physicist at the University of Portsmouth, published a paper in AIP Advances titled The Mass-Energy Information Equivalence Principle. The paper extends Einstein's famous equivalence of mass and energy to include information. Vopson's claim is direct. A single bit of stored information has a finite, calculable rest mass of approximately 3.19 times 10 to the negative 38 kilograms at room temperature. This is derived from combining Landau's principle, which gives the energy cost of erasing a bit, with Einstein's mass-energy equivalence. If erasing a bit costs energy and energy has mass, then a bit has mass. The logic is clean. The number is tiny, but it is not zero. In 2022, Vopson published a follow-up paper also in AIP advances, proposing an experimental protocol to test this. The prediction is specific. When an electron and a positron annihilate each other, standard physics predicts they produce 2 gamma-ray photons, each with an energy of 511 kilo-electron-volts. Vopson predicts there should be 2 additional low-energy infrared photons, each with a wavelength of about 50 micrometers, produced by the erasure of the information content stored in the particles. Those extra photons would be direct evidence that information is a physical quantity, with mass and energy as real as any other property of matter. The experiment has been proposed. As of today, no published results have confirmed or denied the prediction. The photons Vopson predicts would be difficult to detect, swamped by background radiation and the overwhelmingly more energetic gamma rays. But the prediction is falsifiable. It makes a specific, testable claim about what a detector should see. This is not philosophy anymore. This is a laboratory question waiting for an answer. In 2023, Vopson pushed further with a paper on what he calls the second law of infodynamics, published in AIP Advances. The law states that information entropy, the disorder in informational systems, tends to decrease over time or remain constant. This is the opposite of the thermodynamics second law, which says physical entropy increases. Vopson demonstrated this using atomic spin systems, DNA sequences, and mathematical symmetries. His interpretation is provocative. A system in which information entropy naturally decreases resembles a system that is compressing data, pruning waste code, optimizing storage, like a computer managing its memory. Vopson's work is not mainstream consensus. It is published, peer-reviewed, and not retracted, but it sits at the speculative edge of information physics. The important thing is not whether he is right. The important thing is that nobody has shown he is wrong, and the experiment that could settle it has not yet been performed. Meanwhile, the theoretical framework keeps getting reinforced from other directions. In 2012, Silas Bean, Zora Davoudi, and Martin Savage at the University of Washington published a paper titled Constraints on the Universe as a Numerical Simulation. They proposed the most concrete empirical test of the simulation hypothesis to date. Their reasoning starts from how physicists actually simulate quantum systems right now. The gold standard is lattice quantum chromodynamics, or lattice QCD, where space-time is approximated as a discrete cubic grid and quantum fields evolve on that grid. Every lattice simulation has artifact signatures of the lattice structure that show up in the physics. The most well-known artifact is a cutoff in the energy of particles, called the GZK cutoff, above which the lattice cannot accurately represent particle interactions. Bean, Davoudi, and Savage pointed out that if our universe is a lattice simulation, cosmic rays at the highest energies should show two things. First, an energy cutoff analogous to the GZK limit. Second, a directional preference, because a cubic lattice breaks the rotational symmetry that smooth space-time would have. High-energy cosmic rays should arrive preferentially along the axes of the lattice, not equally from all directions. The observed cosmic ray spectrum does show a cutoff near 5 × 10 to the 19th electron volts, known as the GZK suppression. But this is fully explained by conventional astrophysics, specifically the interaction of ultra-high energy protons with the cosmic microwave background. No directional anisotropy has been detected. On its face, This looks like evidence against simulation, but Bean and his colleagues were careful to note that their test assumes a specific lattice geometry, a simple cubic grid. If the simulation uses a different geometry, or an adaptive mesh that refines resolution only where needed, or a non-lattice computational framework entirely, the test would not detect it. The absence of evidence for a cubic lattice is not evidence of absence of simulation. In 2025, Franco Vatsa published a paper in Frontiers in Physics titled Astrophysical Constraints on the Simulation Hypothesis for this Universe. Why it is nearly impossible that we live in a simulation. Vatsa's approach was to estimate the raw computational resources needed to encode the information contained in the observable universe. Using the holographic principle, he calculated the information content on the cosmic horizon and on the surface of the Earth, then compared it to the computational capacity of a hypothetical Jupiter-sized classical computer. His conclusion was that even such a computer would fall 27 orders of magnitude short of encoding the information on just the Earth's surface. That is a devastating number. 27 orders of magnitude is not a gap that incremental technological progress can close. It is not a gap that better algorithms can bridge. If you are trying to simulate the universe with a classical computer, Vatsa's calculation says you cannot. The universe is too information dense. But there is a critical caveat that Vatsa's paper acknowledges but does not resolve. His calculations assume classical computation. They assume that the simulator uses something functionally equivalent to a very large conventional computer. They do not address quantum computation. Richard Feynman conjectured in 1982 that quantum computers can efficiently simulate any local quantum system, a conjecture that Lloyd later confirmed. A quantum computer with 10 to the 90th qubits could, in principle, store all the information in the observable universe. That is a number so far beyond current technology. Current quantum computers have roughly 1,000 qubits, that it is meaningless as a practical prospect. But the point is not practicality. The point is physics. There is no known physical law that prevents a quantum computer of that scale from existing. The universe does not forbid it. It merely makes it very hard. And here is the part that nobody has published yet. The calculation that hangs over this entire discussion like an unanswered question. Nobody has published the quantum version of Vatsa's computation. Nobody has rigorously calculated the computational requirements for a quantum simulation of the observable universe and compared them to the theoretical maximum capabilities of a quantum computer. The classical case is settled. It is nearly impossible, classically. The quantum case is open, and every physicist working in quantum information theory knows it is open, and nobody seems in a hurry to close it. There is another line of evidence that keeps tightening, and it is the one that makes even skeptics of simulation theory uncomfortable. The fine-tuning of physical constants. The standard model of particle physics contains approximately 26 free parameters, numbers like the masses of quarks and the coupling strengths of forces that are not predicted by the theory, but must be measured experimentally. If any of several of these parameters were slightly different, the universe would be uninhabitable. Not just different, empty. The strong nuclear force, if approximately 2% stronger, would bind protons together so readily that hydrogen could not exist and stars could not burn. If 5% weaker, deuterium would be unstable, and the nuclear fusion chain that powers stars would fail at the first step. The ratio of the electromagnetic force to gravity is roughly 10 to the 36th. If this ratio were even slightly different, stars would either burn too hot and die too quickly for planets to form, or burn too cool to produce the heavy elements that make up your body. The mass of the neutron exceeds the mass of the proton by just 1 part in 1,000. If the neutron were lighter than the proton, stable atoms would not exist. And then there is the cosmological constant, which is in a class by itself. The energy density of empty space, as calculated from quantum field theory, should be roughly 10 to the 120th times larger than what is actually observed. The observed value is not zero. It is a tiny, positive number that allows the universe to expand at an accelerating rate without tearing itself apart. The ratio between the predicted and observed values is the most extreme fine-tuning in all of physics. 1 part in 10 to the 120th. To grasp how absurd this number is, imagine a dart thrown at random across the entire observable universe, 93 billion light-years in diameter, and hitting a target the size of a single atom. The fine-tuning of the cosmological constant is more precise than that, by many orders of magnitude. The physicist Martin Rees identified 6 dimensionless constants that must take values within narrow ranges for the universe to contain anything more complex than hydrogen gas. Change any one of them by small amounts, and you get a universe that is either a featureless radiation bath, a lifeless void of black holes, or a cloud of diffuse particles that never clump into stars or galaxies. The universe we actually observe sits in a tiny, improbable sliver of parameter space that allows complexity, chemistry, biology, and you. The standard explanation for fine-tuning is the multiverse. If there are 10 to the 500th different possible universes with different parameter values, as string theory's landscape suggests, then we simply find ourselves in one where the values permit our existence. This is the anthropic principle. It is logically valid. It is also, by Hossenfelder's own criteria, unfalsifiable pseudoscience. The simulation interpretation of fine-tuning is structurally identical. The parameters were selected by a programmer rather than by random sampling across a multiverse. Both explanations account for the data. Neither can be tested. The simulation interpretation is no more pseudoscientific than the mainstream alternative. Max Tegmark, the MIT cosmologist, takes the most radical position with his mathematical universe hypothesis. In a paper published on Arxiv in 2007 and expanded into the book Our Mathematical Universe in 2014, Tegmark argues that the universe does not merely obey mathematical laws. The universe is a mathematical structure. Physical existence and mathematical existence are the same thing. This is not a metaphor. Tegmark literally claims that every mathematically consistent structure exists as a physical universe. If he is right, then asking whether we are in a simulation or a real universe is like asking whether the number 7 is real or computed. The question does not make sense. Mathematical structures do not need to be computed by anyone. They exist as mathematics. The distinction between a simulated universe and a physical universe dissolves not because simulation is proven, but because the categories cease to apply. Tegmark's idea has been criticized. Peter Woit at Columbia has called it not even wrong. Other physicists find it too speculative, too detached from testable predictions. But Tegmark is a tenured professor at MIT. His papers are published in refereed journals, and his hypothesis sits within a growing family of serious proposals: Wolfram's Ruliad, Tooft's cellular automaton interpretation, Wheeler's it, from bit, all converging on the same uncomfortable territory. The boundary between physics and computation is not sharpening with new research. It is dissolving. David Chalmers, the Australian philosopher who coined the phrase "the hard problem of consciousness," at the 1994 Tucson Conference, published Reality Plus in January 2022. His argument inverts the usual anxiety about simulation. Chalmers argues that even if we are in a simulation, our reality is genuine. Virtual reality is genuine reality. The objects in a simulation are not fake objects. They are digital objects made of bits rather than quarks, but no less real. A quark, after all, is already a mathematical abstraction. It has no color, no texture, no substance in the everyday sense. It is a pattern of quantum fields described by equations. A bit in a simulation is also a pattern described by equations. Why should one be real and the other fake? Chalmers assigns roughly 25% probability to living in a simulation. His reasoning is careful, his credentials impeccable. He has a track record of being right about things that make other philosophers uncomfortable. In 1998, he bet neuroscientist Christoph Koch a case of wine that the neural correlates of consciousness would not be fully identified by 2023. In June 2023, the results came in. Chalmers won. The hard problem persists. Nobody knows what consciousness is or where it comes from. And if we do not understand the most basic feature of our own experience, our confidence that reality is what it seems should be calibrated accordingly. Tooft himself has continued pushing. In 2016, the Nobel laureate published the Cellular Automaton Interpretation of Quantum Mechanics, a full-length book arguing that quantum mechanics emerges from deterministic, classical cellular automaton processes at the Planck scale. His approach is what physicists call superdeterministic. The outcomes of all quantum measurements are predetermined by initial conditions, eliminating the apparent randomness that makes quantum mechanics so strange. The physics community is largely skeptical, but Tooft's response to the skepticism is essentially, "I proved the electroweak theory was renormalizable when everyone said it could not be done. I have earned the right to be taken seriously on speculative ideas." And then there is Stephen Wolfram. Wolfram earned his PhD from Caltech at age 20, became the youngest ever MacArthur Fellow at 21 in 1981, and created Mathematica, one of the most widely used computational platforms in science. In 2002, he published A New Kind of Science, a 1,280-page book, self-published after 10 years of work, arguing that the complexity of nature arises not from complicated equations, but from ultra-simple computational rules applied repeatedly. A handful of lines of code, iterated billions of times, can generate structures of arbitrary complexity. The physics community was largely hostile. Steven Weinberg noted that no real-world system had been satisfactorily explained using Wolfram's methods. Freeman Dyson remarked that there is a tradition of scientists approaching senility to come up with grand, improbable theories, and that Wolfram was unusual in that he was doing this in his 40s. Wolfram was not deterred. In April 2020, he launched the Wolfram Physics Project, a public research initiative proposing that the universe is a massive hypergraph, a network of abstract nodes connected by relations, continually updated according to simple rewriting rules. In this framework, space, time, matter, energy, and even the laws of physics themselves emerge from the application of these rules to the hypergraph. Space-time is not fundamental. It is a consequence of computation at a level below space-time. Wolfram introduced the concept of the Reuliad, which he defines as the entangled limit of everything that is computationally possible. The space of all possible computations and their relationships. Our physical laws, in this view, arise from the particular way conscious observers like us sample the Reuliad. Different observers, embedded differently in the computational structure, would experience different physics. The physics community has criticized the project for producing non-quantitative results, for bypassing peer review, and for claiming more than the framework delivers. These criticisms are fair, but the structural claim that reality emerges from computation rather than the other way around is not unique to Wolfram. It is the same claim, expressed differently, that Wheeler made with it from bit, that Zuse made with rechnender Raum, that Tooth makes with his cellular automaton interpretation, and that the holographic principle implies about the emergence of space-time from boundary information. The question these frameworks collectively raise is not whether any individual one is correct. The question is why so many independent approaches built on different mathematics by different people in different decades keep arriving at the same structural conclusion. The universe looks from every angle physicists have examined, like something that is being computed. There is one more piece of this, and it sits at the smallest scale physics can currently probe, the Planck length, approximately 1.616 times 10 to the negative 35th meters, and the Planck time, approximately 5.391 times 10 to the negative 44th seconds, define the boundary where classical space-time breaks down. These are not just very small numbers. They are the scales at which quantum gravity effects dominate, where general relativity and quantum mechanics collide, where our current theories stop making sense. The Planck scale matters for the simulation question because it sets the resolution limit of reality. Any attempt to probe distances shorter than the Planck length would concentrate enough energy in a small enough region to create a black hole, which would swallow the measurement before it could be completed. The universe, in a precise physical sense, has a minimum pixel size. You cannot zoom in past the Planck scale. There is nothing to see below it. Or more accurately, the question of what exists below it may not have a meaningful answer. Loop quantum gravity, developed by Carlo Rovelli and Lee Smolin beginning in the late 1980s, predicts that area and volume are quantized. Space is not smooth and continuous. It is woven from discrete loops connected into structures called spin networks, with a minimum meaningful area on the order of the Planck area, roughly 10 to the negative 70th square meters. If this is correct, then space-time is not a continuum. It is a grid, a lattice, a discrete structure with a finite number of cells. The observable universe, viewed through the holographic principle, has a cosmic horizon whose surface area, divided by the Planck area, gives approximately 10 to the 122nd bits. This is consistent with Lloyd's independent estimate of 10 to the 120th operations. The numbers converge from completely different directions, one from information theory and one from quantum gravity, and they arrive at the same conclusion. The universe has a finite, calculable number of degrees of freedom. It is not infinite. It is not continuous at the deepest level. It is discrete, bounded, and countable. In 2011, the European Space Agency's integral satellite searched for evidence of Planck-scale discreteness by looking for energy-dependent dispersion in gamma-ray bursts. Photons of different energies traveling across billions of light-years should arrive at slightly different times if space-time is granular at the Planck scale. Integral found no such dispersion, placing limits 13 orders of magnitude below the Planck length. This seems to push against the idea of a discrete space-time, but the interpretation is subtle. The test constrains specific models of discreteness, particularly those that violate Lorentz invariance. It does not rule out all forms of Planck scale structure, and several models of discrete space-time are fully compatible with Lorentz symmetry. The honest summary is this: we do not know whether space-time is continuous or discrete at the Planck scale. The question is open, but the convergence of evidence from the Bekenstein bound, from the holographic principle, from Lloyd's calculations, from loop quantum gravity, from the finite computational capacity of the observable universe, all points toward discreteness, toward a universe with a finite resolution, toward a reality that is, at its deepest level, built from a countable number of discrete elements interacting according to rules. If that sounds to you like a description of a computer, it should, because it is. Every year, the list of credentialed physicists and philosophers who take some version of the computational universe seriously grows longer, not shorter. The math is not converging on debunking. The math is converging on a conclusion that nobody is comfortable saying out loud. And the pattern is clear to anyone paying attention. The question is no longer whether the simulation argument can be defeated. The question is whether the distinction it relies on, the distinction between real and simulated, survives contact with the physics. Jacob Bekenstein died on August 16, 2015 in Helsinki, Finland, while attending a physics conference. He was 67 years old. He had just received the American Physical Society's Einstein Prize, one of the highest honors in theoretical physics, for his work on black hole entropy. Scientific American's obituary called his legacy pretty damned impressive for someone you have probably never heard of. He had proposed as a 25-year-old graduate student that black holes store information on their surfaces. His advisor Wheeler supported him. Hawking attacked him. And then Hawking's own mathematics vindicated him. Bekenstein spent his entire career proving that information is physical, that it has entropy, that it has limits, that it matters. He never used the word simulation. He did not need to. The physics he built is the foundation on which every uncomfortable question about the nature of reality now rests. Wheeler died on April 13, 2008, at age 96, at his home in Hightstown, New Jersey. He spent the last decades of his life pushing it from bit, with the urgency of a man who knew his time was short, and the question was too large to leave unanswered. His participatory universe, the idea that reality requires observation to exist, remains one of the most provocative interpretations of quantum mechanics ever proposed. And it came from a man who spent 60 years wondering if his brother Joe needed to die, if the past was truly fixed, if time and existence are what they appear to be from the inside. Konrad Zuse died on December 18, 1995, in Hossenfelder, Germany. He was 85. He had lived long enough to see the computer revolution transform the world, but not long enough to see his Rechnender Raum taken seriously. The man who built the first computer in his parents' living room while the world burned also became the first person to propose that the cosmos runs on computation. And the world ignored him twice. Bostrom is still alive, still at Oxford, still publishing. In 2023, his career was nearly derailed when a 26-year-old email surfaced in which he had used racist language. He apologized, calling the message disgusting. The email had been sitting in a digital archive for over 2 decades, a piece of information that could not be erased, that resurfaced at the worst possible moment. There is something almost too on the nose about the man who asked whether we live in a simulation, having his own past resurrected from a machine's memory. A ghost in the archive. The universe keeping perfect records once again. Now here is where this lands. Everything I have told you in this video is published, peer-reviewed, mainstream physics. The Bekenstein bound is not controversial. The holographic principle is not fringe. Quantum error correction in space-time is accepted by the leading researchers in quantum gravity. The resolution of the black hole information paradox, confirming that the universe preserves information perfectly, is consensus physics. Landauer's principle has been experimentally verified multiple times. Lloyd's calculation of the universe's computational capacity is textbook material. The measurement problem and the informational basis of quantum outcomes are the central, unresolved questions of quantum mechanics. None of these results were produced to support the simulation hypothesis. They emerged independently from different subfields over 3 decades, driven by completely unrelated research programs. Black hole physicists did not set out to prove that reality is informational. Quantum information theorists did not set out to find error-correcting codes in spacetime. Experimentalists verifying Landauer's principle were not thinking about simulation theory. The convergence is accidental, and that is what makes it so much more difficult to wave away. Let me be precise about what the physics says and what it does not say. The physics does not say we live in a simulation. There is no experiment that could prove that, and anyone who tells you otherwise is selling something. The physics does not confirm Bostrom's trilemma, which is a logical argument that stands or falls on its own premises independently of empirical data. What the physics says is this: the universe contains a finite amount of information, bounded by the Bekenstein limit. That information is physical, with measurable thermodynamic consequences, as proven by Landauer. The universe processes this information according to laws that are, by the mathematical definition, computational. As quantified by Lloyd, the information in any volume of space is fully encoded on its 2-dimensional boundary, per the holographic principle. The structure of space-time is that of a quantum error-correcting code, per Almheri, Dong, and Harlow. Information is never destroyed under any physical process, per the resolution of the black hole information paradox. And physical outcomes are determined not by forces or interactions, but by the availability of information, per the measurement problem and the delayed choice experiments. Each of those statements individually is unremarkable. Physicists work with them every day, but collectively, they describe a universe whose fundamental architecture is indistinguishable from a computational system, not analogous to one, indistinguishable from one. And the distinction between a universe that is a computation and a universe that is being computed is not a distinction that appears anywhere in the equations. That is the part nobody wants to say. Not because it is wrong, but because it is professionally dangerous and philosophically vertiginous. The question was never, are we in a simulation? The question is what real means when the laws of physics are informational, when space-time is a code, when the universe keeps perfect records, and when observation determines reality. If real means made of stuff that is not information, then nothing is real, because at the bottom of every physical theory, there is only information. If real means not being computed by someone else's machine, then you need to explain what makes computation by physics laws different from computation by a simulator. And nobody has been able to do that. Not because they have not tried, but because the distinction does not appear in the mathematics. Hossenfelder calls the simulation hypothesis pseudoscience because it cannot be falsified. She is right about the unfalsifiability, but the informational foundations of physics are not pseudoscience. They are confirmed, replicated, published in the highest tier journals in the world, and those foundations dissolve the boundary between simulated and real so completely that the category of pseudoscience loses its grip. You cannot call an idea unscientific when the science itself eliminates the conditions under which the idea would be distinguishable from reality. The simulation hypothesis might be unfalsifiable, but so is the hypothesis that we are in base reality. Neither one makes a different prediction. Neither one leads to a different experiment. The asymmetry in how they are treated, one as obvious common sense and the other as laughable speculation, does not come from the physics. It comes from human comfort. And physics does not care about human comfort. The 2017 headline said it was debunked. It was not. The Bayesian analysis says 50%. The physics says the question may be incoherent. The people who understand the math best are the most reluctant to talk about what it means. And every year, the results come in from black hole thermodynamics, from quantum information theory, from the foundations of space-time, and every year they point in the same direction, not toward proof of simulation, toward the dissolution of the distinction between simulation and reality, toward a universe where real and computed are not opposites but synonyms. Wheeler lost his brother in 1944 and spent the rest of his life asking whether reality is built from information. Zuse built a computer in his parents' living room and spent the rest of his life arguing that the cosmos runs on one. Bekenstein contradicted Hawking as a graduate student and proved that the universe's information is finite and physical. They were all working on different problems. They never coordinated, and they converged on the same conclusion from 3 different directions. The simulation argument was never debunked. The math is not settling down. And the reason nobody will tell you what the physics of information actually implies is not that the implication is too speculative. It is that the implication is too clear. The universe stores information on compressed surfaces. It projects 3 dimensions from 2. It corrects its own errors. It never destroys a single bit. It only resolves outcomes when information is extracted. And the distinction between a universe that does all of this because it is a computation and a universe that does all of this because it is being computed does not appear anywhere in the physics. It never has. And with every new paper, every new result, every new confirmation that information is the bedrock of reality, it becomes less likely that it ever will.